Suppose till now what we were doing was, suppose we have to uh, analyze a circuit, we should just do this. Suppose you have an inductor, okay, and if you connect a voltage source, suppose, what is going to happen? Okay, is what we were looking at. Now here what we do is, along with this application of voltage, we bring in a switch which decides when this voltage has to be applied, or the time when this voltage is being applied. So this is the switch which can be closed or it can even be opened. If it goes, see, suppose you have a switch like this. Okay, so this is a switch. If the symbol is this, it is switch being closed. It's not switch closed, but switch being closed. So all these terminologies would make a lot of difference. Understand? Similarly, if you have a switch like this, and if the arrow is shown like this, then the switch is being opened. It's being opened. It's not opened. Makes a difference. Understand that? So we bring in such timing analysis here in transient analysis. Okay, so when the switch is being closed, okay, before the switch was closed, what was actually the scenario? Was there a current flow or was there not a current flow? So all these things need to be analyzed. So what we're doing is, before the switch closure, what was the thing, and after the switch closure, what is the thing? Understand that? So what we do is, we analyze it like this. We analyze the condition, we bring in time. We bring in time. Okay. Now t equal to 0 is a reference time. Okay. We say t is equal to 0 plus. T is equal to 0 minus. These are all the times. And after this time is elapsed for certain duration, we go for something like t equal to infinity. Understand? So the analysis here are referred to as initial conditions. Everybody okay with that? And the analysis at t equal to infinity is final condition. Everybody is okay with this? So we bring in the time analysis here in this chapter. Fine. So this is what is important to be understood here. We bring in time analysis. Okay, and when we bring time analysis, we talk about the initial conditions and the final conditions. Understand that? See here, we talk about the initial conditions. That means at t equal to 0, 0 plus 0 minus. What is going to happen? 0 plus means what? Suppose the switch is being closed at t equal to 0. At t equal to 0, switch is being closed. So that means at t equal to 0 minus, what was the switch? Switch was open. At t equal to 0 plus, switch is just closed. Here, the switch is closed. Here, the switch is being closed. That way, at t equal to 0, the switch is being closed means at t equal to 0 minus, the switch is open. Okay. So at t equal to 0, the switch is being closed means at t equal to 0 plus, the switch is just closed. Everybody understand that? And after some time has gone by, we say it is closed. Understand? So this is the analysis. Now when the switch is closed at t equal to 0, it was open. So when it was open, was there a current flow? Then if that current flow was not there when it is open, after the switch is closed, is there a current flow? Or the conditions are going to be the same as it was when it was open? So all these is what we are going to learn in this particular chapter, that is transient analysis. Everybody understand that? So module 3 is transient analysis, wherein we are bringing in all these timing analysis into action. Understand that? So what we'll do here is finding the initial conditions and final conditions of the currents and voltages. But yes, you should understand we play with the inductors and capacitors. Understand that? So we need to now look at something called as this: initial and final conditions in L, inductor, capacitor and resistor. Initial and final conditions in LCR, in inductor, in capacitor and the resistor. This is something that we'll do now. Everybody's okay with that? Yeah. Let's move on now. Let's now just see the initial conditions in R. Everybody's okay with that? Just take down this initial, so not R, initial conditions in L we shall see first. Initial and final conditions in in inductor is what we are looking at. L. Understand it? Everybody? Is everybody okay with this? So we shall see this. Fine. Everybody just copy down. Okay. Let's note all the things that we are doing today. Fine. So what we are doing is seeing the initial and final conditions in inductor first. Okay. So let's write the circuit diagram like this. Everybody just copy down this. What we're doing is we have a voltage source like this. Okay. Then let's bring in a switch. After the switch, let's connect an inductor L. Okay. Now this is a switch. Let's say we show it like this. And we write t equal to 0. What is the meaning of this? What is the meaning of this? Okay. Everybody just look at the symbol of switch indicates that the switch is being closed at t equal to 0. Everybody understand? This particular switch symbol, this is symbol of the switch. Okay, and this is the voltage applied. This is the voltage applied. The symbol of the switch very clearly shows that the switch is being closed at t equal to 0. Understand? So that means what? That is at T equal to 0 minus, what was the condition of the switch? Switch was closed. Sorry, switch was open at T equal to 0 minus. Understand that? So T equal to 0 is the time at which the switch is being closed. Fine. The switch was open at T equal to 0 minus is what is the indication of that. Okay. Then at T equal to 0 plus, what is the condition of the switch? Switch is, we should not say closed, switch is just closed. Not much time has passed by after the closure. Soon after, the switch is closed. Switch is just closed, we say, right? So what is the meaning of that? Soon after the closure. Closure means closing of the switch. Soon after the closure. So these are all the different terminologies that we have to be very careful about. Understand? So at T equal to 0, the switch is being closed, which means that at T equal to 0 minus, the switch is open. At T equal to 0 plus, the switch is just closed. Okay. Now, when this was open, was there a current flow is the question. Okay. So let's say there is a current. Let me just indicate I of T. Okay. And this is also V of T you can take. Since we are bringing timing into consideration. Okay. So at T equal to 0, what is I of T? I of T is I of 0. At T equal to 0 minus, what is I of T? I of T is I of 0 minus. It is something like that. So now you should answer at T equal to 0 minus, was there a current flow? Is the question that is being asked. No, because when the switch is open, the circuit is incomplete. So there the current will not flow. But soon after the switch is closed, will this current flow at T equal to 0 plus? When the switch is just closed, that means at T equal to 0 plus. That is, what is I of 0 plus? Would I of 0 plus be there? So all these questions we need to be answering. Get that point? Okay. Now, when we consider the inductor, we should understand inductor and capacitor are, just see this. Don't take down. Inductor and capacitor are storage elements. Storage elements. Understand that? L stores current and C stores voltage. Understand that? So L and C both are storage elements. Okay. Capacitor stores voltage and inductor stores current. So since we are talking about the initial and final conditions of the inductor, in inductor we do the current analysis. Okay. When we do this same analysis for capacitor, we do the voltage analysis. Is that okay with you, everybody? Okay. So in inductor, we do the current analysis because inductor is a current storing element. What? L is current storing element. Current storing element. Okay. Similarly, C is voltage storing element. Okay. So this is very important. So since we are talking about L here, okay, what do we do? What do we do there? We do the analysis of current. Understand? So let's analyze the current through inductor. Is everybody okay with that? Now, let's not show all these in your solution when you're asked to give the initial and final conditions. Okay, this is all just for your reference. Okay, but this needs to be told. The switch is being closed at t equal to 0 is important. Now let's see the uh, current analysis. Okay, let's analyze the current in this device. So at t equal to 0, the switch is being closed. Understand that? At t equal to 0, the switch is being closed. So suppose if there is a current flowing, suppose if there is a current flowing, how would that current look like is the question. How would that current look like is the question. So what is the equation for current that is flowing through the inductor? Equation for current that is flowing through the inductor. Okay, so let's write current through the inductor through L, let's say. Okay, is what, let's say I of t, because I'm saying I of t because I'm not saying current through the inductor when switch is closed. No, I'm not saying that. I'm not saying current through the inductor when switch is open. No, I'm not saying that. I'm just saying current through L. It could be when the switch is open, or it could even be when the switch is closed. Okay, so I'm making that current a generalized one. Okay, so when I bring in those current conditions, I'll say whether it was open or closed at in this position. Okay, so I of t. So I of t is given by 1 by L times integration of, okay, V of t dt. What is V of t? V of t is the applied voltage. Everybody understand that? V of t is the applied voltage. Okay. Now I of t is the current flow. Fine. Okay, now everybody just concentrate here. Yeah. So let's see this, everybody. Now, after we have the equation for I of t. See, I of t is an integral equation, you should remember. I of t is a integral equation. It's 1 by L, okay, integration V of t dt. And when we integrate, okay, we say the limit of integration is minus infinity to some time t. I don't know what is that time. Minus infinity to t. Understand that? Now the same I of t. See, same I of t can be written as what? 1 by L you can keep out. I hope everybody is copying this. 1 by L minus infinity to 0 minus. Fine. If I write minus infinity to 0 minus V of t dt here, what can I write here? Seeing this, what you would say? You would say it is from 0 minus to t V of t dt. Is this understood, everybody? Yes. What we have done, suppose I bring in this 0 minus interval minus 0 minus infinity to 0 minus I bring. Okay, so in this interval, was this switch closed? See here, was this switch closed in this particular interval? Interval is from where to where? From minus infinity to 0 minus. This is t equal to, always you should remember, this is, we're doing timing analysis. So from minus infinity to 0 minus. 0 minus is where? 0 minus is switch was open at 0 minus. That means at t equal to minus infinity also the switch was open. The switch is just closed at t equal to 0, or the switch is being closed at t equal to 0. Understand that? That means at 0 minus, what was the switch? Switch was open. So that means this current that we have written, this current we have written is the current uh, that is when the switch was open. Everybody understand that? Now, what is this? This is the current. Let me just write that one by one. Let me bring all this as two currents. Okay, I'm going a little slow because you need a lot of understanding here. Okay, so I'll say 1 by L times this and 1 by L times this. So we are doing this analysis when, what is this? This is I of 0 minus before the switch is closed. Understand that? And what is this? This is, I'll just say, if this is I of t, if this is I of t, okay, then therefore what is I of 0 plus? This is I of 0 minus. Why this is I of 0 minus? Why this is called I of 0 minus? I of 0 minus is the current that is flowing when the switch was open. Okay, that means from minus infinity to 0 minus, the switch was open, so I of 0 minus only was flowing. So this is I of 0 minus. Okay, plus, see what I do now, it is 1 by L integration of 0 minus, what has happened to t now? See here, this was t, now t has become 0 plus now. So what should I be writing in this case? T has to be replaced by 0 plus. Okay, v of t dt, or v of 0 plus you can say, or you can say v of t dt, not a problem. Now what's happening? 0 minus to 0 plus. So this was from minus infinity to 0 minus. It's considerable duration. But what is this duration 0 minus to 0 plus? Everybody just understand this. Switch is being closed at t equal to 0 means, okay, 0 minus 0 plus are just, they're almost the same, but they're not same, they're almost the same. Understand that? So it is very small duration that is there between 0 minus and 0 plus. So that means we can say they are almost same. And when there is no big time being passed by, okay, nothing actually happens. So what can we say? This actually is 0. 0 minus to 0 plus, the duration is so small that nothing actually happens. We don't analyze anything in that small duration. That's why we consider this as 0. We ignore it. Everybody understand? I again repeat. 0 minus to 0 plus is such a small duration that it is almost 0 time. Okay? Or you can say it is almost no time. So in no time, nothing happens. So that's why we don't go for analyzing this particular term. We say the duration is very small and nothing actually happens in that very small duration. So that's why we just ignore this part. So if we ignore this part, what would happen? What would happen? See here, this implies that our I of 0 plus is going to be I of 0 minus. This is very important result. Initial condition. This is the initial condition. Understand that. This is the initial condition. Fine. Let's find out the final condition. Okay. But just understand what is happening again. Fine. Again, let's try understand what we have done so far. Let's just take all these off. Yeah. I'll explain it again. See here. Current through L is given by this. Is that okay with you, everybody? Current through L is given by this particular equation. Okay. Now what we need to do? See here. This is the current through inductor. Now current through the inductor can be split into two parts. One part is from minus infinity to 0 minus. Another part is from 0 minus to t. Okay. Now let's just analyze this particular equation at t equal to 0 plus. So we can write that. Therefore, at t equal to 0 plus, what's happening? At t equal to 0 plus, I of t would become I of 0 plus. And anyways, this is I of 0 minus. That is, this is the current that is flowing when the switch was open. Understand that? And what is this at 0 plus? At 0 plus, it would become 0 minus to 0 plus. And this particular duration is so small that nothing actually happens, and we just ignore this part. So when we ignore this part, what you're seeing is I of 0 plus would be equal to I of 0 minus. So what is this actually telling you? It actually is telling you that the current that flows through the inductor, okay, is actually equal to the current that was there before the switch closure. That means at I of 0 plus, whatever is flowing, that current is actually equal to the current that was flowing before the switch closure. That means soon after the switch closure, what would be the current? The current would be same. Soon after the switch closure, the current would be same. That means the current would not change instantaneously through the inductor. For current change to be there, okay, this switch has to be closed for a long duration. When the switch is closed for a long duration, then I of 0 plus is not equal to I of 0 minus. But when the switch is just closed, okay, I of 0 plus would be I of 0 minus only. So there would not be any change soon after the switch is closed. But if the switch is closed for a long duration, then only there would be a change in the current that flows through the inductor. Is everybody okay with that? So what does this indicate? What does this particular equation indicates? This indicates that current through the inductor does not change instantaneously. Yeah. So very important is this. It does not change instantaneously. Okay. So you should remember this. It does not change instantaneously. Okay. Now this is initial condition. Fine. Now what is going to be the final condition? So what we have found out is initial condition through inductor. Now we shall find out the final condition. Understand that? Okay. Now let's take down this. What is the meaning of this? You've understood now. Before the switch closure, whatever was the current flowing, soon after the switch closure, the same current would flow. Understand that? So that is what we have learned. Now, what is the final condition? Let's understand the final condition. Okay, so everybody just copy it down. To find the final condition, to find the final condition, we consider the differential equation. We consider the differential equation. Okay, this again is something that you should understand. To find the final condition, okay, we consider the differential equation, mind you. We consider the differential equation. So which equation do we have with us? We have an integral equation here, right? So how to make this differential equation? So this is integral equation. How to make this differential equation? So this is equation number one. Let's everybody call this as equation number one. Okay, so call this equation as number one. Okay, so what would happen to this equation number one if we differentiate this? Okay, so by differentiating, therefore by differentiating equation 1 implies, what does this imply if you differentiate this, okay, with respect to t, I mean, so it's di by dt. Let's not take this t into consideration. Di by dt, what would happen to this integral if you differentiate? If you differentiate, the integration is cancelled. Understand that? So how would this equation number one be looking like? Just see here. I'm differentiating 1 with respect to t. I'll just write that here. Fine. See, it looks like di by dt, that of t I'm not writing. Okay, di of dt. Okay, 1 by L times what? V. So this implies what? This implies V is L times di by dt. So we had a integral equation to begin with for current flowing through the inductor. So for initial conditions, we considered this. For final conditions, what they say, for final condition, we should consider the differential equation. So what we can do from this, we have to differentiate this to have the differential equation. So if you differentiate, so this is what you're going to have. Okay, so just write this to have the analysis for final condition. Okay, so let's have that here. Everybody okay with this? Now, what is final condition means? Final conditions means what? Let me write that here. See here, final condition means at t equal to infinity. Okay, or let's say at t equal to infinity is what we need to write. This is the infinity. At t equal to infinity is what we need to look at. Final conditions means at t equal to infinity, what? At t equal to 0, this switch is just closed. At t equal to 0 plus, this switch is just closed. At t equal to infinity, what is happening? Final condition is what we see at t equal to infinity. That means what? After the switch is closed for a long duration, the switch is closed for a long duration. Let me write just here. Final condition, switch closed for long duration. Is the meaning of this. And when the switch is closed for a long duration, a condition prevails. What is that condition? There will not be any transients. Okay, so everybody just understand here. 0 minus 0 plus is within no time. At 0 minus, the switch was open. The switch is being closed at 0. So that means at 0 plus, the switch is just closed. At t equal to infinity, the switch is closed for a long duration. Fine. So that is the analysis we are making. So at t equal to 0 plus what happens we have seen. Now at t equal to infinity what is going to happen is what we are seeing. Okay. Now at t equal to infinity, therefore at t equal to infinity, what is true? V of infinity, right, is equal to what? L di of infinity by dt. Fine. Now you can write t, not a problem. You can write t. Okay, here. Fine. Now, can anybody tell me what is this particular thing going to be? What would be I if there is a current flow? If there is a current flow, what would that current be after the switch is closed for a long duration? Would there be any change in the current? Is the question. Suppose after the switch is closed, just after the switch is closed, nothing happens. But after the switch is closed for a long duration, whatever was the current, the same current continues to flow, and that current would not increase or decrease after the switch is closed for a long duration. Everybody understand? Whatever is the current that is flowing after the switch is closed for a long duration, the same current continues to flow. Whether you keep it closed for 1 minute or 2 minutes or 10 minutes or half an hour, the same current is flowing. That means, don't you think the current is constant? Okay. So because of that, because the current is constant, okay, we say this particular entity will go zero. Okay. So this will go zero because I is constant. Understand that? So if this goes zero, what would happen to this? V of infinity would be, okay. See this, V of infinity is zero means what? V of infinity is zero means what would be the circuit for zero voltage? The circuit for zero voltage is realized by a short circuit. Okay. What would the circuit for an open circuit? What would the circuit when the current is zero? When the current is zero, the circuit is realized by an open circuit. When the voltage is zero, the circuit is realized by short circuit. Understand that? So this is final condition. This is final condition. Everybody okay with that? So we have obtained the initial and final conditions like this. Fine. So we shall just try summarize all this. So how to summarize that? Let's summarize. Summary in terms of a table. We shall see the summary. What is that? Suppose at t equal to 0 minus. Fine. At t equal to 0 minus, we shall see what happens. At t equal to 0 plus, let's see what happens. And at t equal to infinity, let's see what happens. Okay. Now, at t equal to 0 minus, suppose there is an inductor. Condition 1. Suppose there is an inductor. Okay. With no current flow. Inductor with no current. So that means, what is the meaning of that? If through the inductor at 0 minus there is no current, means what is the meaning of that? The meaning of that is I of 0 minus is 0. That is the meaning of that. Is everybody okay with this? at t equal to 0 minus, through the inductor there is no current flowing, means I of 0 minus is 0. Understand that? If that is the case, okay, what do you think I of 0 plus should be? What do you think I of 0 plus should be? Here, I of 0 plus would also be 0. Is that understood, everybody? Why is that so? Because see here, I of 0 plus is equal to I of 0 minus. Since I of 0 plus is equal to I of 0 minus, if at t equal to 0 minus, I of 0 minus is 0, then I of 0 plus would also be 0. That means before the closure of the switch, if the current is 0, just after the closure of the switch, the current is 0, because the current would not change instantaneously. Current through the inductor would not change instantaneously. So no current at t equal to 0 minus means no current at t equal to 0 plus. So no current is realized by what? No current is realized by what? What can you realize this inductor when there is no current flowing? It is as good as this. Everybody see here? It is as good as this. What is it? It is open circuit. Everybody understand that? At t equal to 0 minus, there is an inductor, but there is no current flowing. So that means at t equal to 0 plus, the inductor can be replaced by an open circuit. Is that okay with you? At t equal to infinity, what is happening? T equal to infinity needs to be decided by seeing the voltage. What is V equal to infinity? V of infinity. V of infinity is 0. Why we need to consider this when we are seeing the final condition? Because when we are seeing the final condition, everybody should remember, we look at the differential equation. Okay, and differential equation very clearly has given us this particular result. V of infinity, the voltage after the switch closure is going to be 0. That means what is 0 voltage? 0 voltage is short circuit. Is this understood, everybody? 0 voltage is short circuit. Then what is the second condition? What is the second condition? Second condition is there is a inductor, okay, and through the inductor, suppose there is a current I naught flowing. What is the meaning of this? Suppose at I equal to 0 minus, there is a current I naught flowing. If this is happening, if there is a current I naught flowing at t equal to 0 minus, so that means what is I of 0 plus? I of 0 plus would also be I naught. Fine. So what can I replace my inductor by? If this is the case, the inductor can be replaced by a current source. Fine. A current source I naught. Why? At t equal to 0 minus, there is a current I naught flowing. So at t equal to 0 plus, the same current would be flowing. So that means the inductor is as good as a current source with current I naught. Understand that? So this is how it happens. Fine. Now, what is the resistance here? At this, resistance is 0, right? Resistance is 0. Okay. So here what they do is they realize L like this. It is short circuit and current I naught comes like this. So this is how they say the inductor can be realized at the final condition when the current I naught is flowing. Okay, if there is a current flow, that current flow will not change instantaneously. Okay, but that current would change maybe when we keep the same condition for a long time. Okay, and that change in current is shown like this. Okay, there would be a current flowing initially, but when a short circuit comes, that current may decrease because the whole of the current. This is little difficult to explain rather. Okay, V of infinity when current is flowing. Okay, so just remember this. Okay, as it is. Fine. I'll again be revisiting this with a better example. Okay, so this is how we can summarize. Fine. Yeah. Let's see this. So how is the circuit going to look like? The circuit is going to look like this. Everybody just copy down this. We have a voltage source. Fine. We have switch. Then instead of inductor now, let's have capacitor. Fine. This is the capacitor. Voltage applied. Okay. The current I. So let's call this as I of t and this as V of t. Okay. Here also there is a switch which is being closed at t equal to 0. And what do we analyze? We analyze the voltage across the capacitor. And what is the voltage across the capacitor? Voltage across the capacitor is the voltage that is applied here. Because see, whatever is the voltage that is applied, soon after the switch is closed, whole of this voltage would come and drop across this C. Okay, so the applied voltage and voltage across the C when this switch is closed is the same. Get that point? So we analyze the voltage across the capacitor now because capacitor is a voltage storing device. Understand that? So let's everybody write this. Since okay, let's go now. What is voltage across the capacitor? Okay, everybody write that. Voltage across the capacitor is Vc. Let's not write Vc, it's V of t only. Okay, what is V of t? V of t is 1 by C integral t equal to what? 0 minus infinity to t. 1 by C minus infinity to t. Okay, I of t dt. Compare it with the current through the inductor equation. Current through the inductor equation is also an integral equation. See, current through the inductor is also integral equation. It's 1 by L times integral of V of t dt. Okay, and here voltage across the capacitor is integral equation, and it goes like this. Voltage is replaced by current, and the inductor is replaced by capacitor. Let me just show you that equation here. So this is the current through the inductor. Current through the inductor is this: I of t is equal to 1 by L integral t equal to minus infinity to t v of t dt. So this is how we had written the current through the inductor. Okay, let's compare these two equations. Current is replaced by voltage, inductor is replaced by capacitor, and voltage is replaced by I. So voltage and current are interchanged, L and C are interchanged. Okay, and both are integral. the current through the inductor is integral because inductor stores current. Voltage across the capacitor is integral because capacitor stores voltage. Okay, so you should see what capacitor stores voltage. So voltage is an integral equation. Voltage across the capacitor is an integral equation. Current, inductor stores current. That's why current through the inductor is an integral equation. Is everybody okay with this? Okay, this is just for reference I gave. So let's delete this. So this is how it is going to look like. Now let's do the same analysis. What we can do, this implies what? This implies V of t is equal to 1 by C times. Suppose I go from minus infinity to 0 minus I of t dt. Then we need to have another term here which goes from t equal to 0 minus to t. Okay, I of t dt. Fine. Now at t equal to 0 plus, at t equal to 0 plus, how would it look like? It look like V of 0 plus. Okay. Now what would be the voltage across the capacitor? Let me write that here. What would be the voltage across the capacitor? Okay, when the switch is not closed. That means at 0 minus, do you think the switch was closed? No. That means this is what? From minus infinity to 0 minus. 0, yeah, it's not minus infinity. Infinity minus to 0 minus. So what is that? What is this term? This is voltage across the capacitor. What is this? This is voltage across the capacitor at t equal to 0 minus. Fine. What would this be? What would this look like? See here, this would be V of 0 minus plus 0. This would not be there. This would go 0 plus. What does it look like? It 1 by C times t equal to 0 minus to 0 plus I of t dt. Let's write. So again, from 0 minus to 0 plus, what's happening is negligible because it's almost no time. So this we say is 0. So this implies that V of 0 plus is actually equal to V of 0 minus. Is everybody okay with this? So in inductor, when we analyzed the current through the inductor does not change instantaneously. That's why I of 0 plus is equal to I of 0 minus. Similarly, voltage across the capacitor would also not change instantaneously. So that we need to write. So this indicates that, everybody just take down. This indicates that voltage across the capacitor does not change instantaneously. So voltage across the capacitor would not change instantaneously, and similarly current through the inductor would not change instantaneously. Okay, now this is initial condition. Let's find out the final condition. Okay, so to find the final condition, what we need? We need differential equation. So where is the differential equation coming from? So if you differentiate this, you will get the differential equation. Why differential equation? Because the final condition, to find the final condition, that means at t equal to infinity, we consider the differential equation. So this is the idea. Okay, so we have the integral equation here. So how to have the differential equation? Call this as equation number 1 again. So this is equation number 1. Okay, so differentiate equation number 1. How does it look like if we differentiate? To find the final condition, differentiate equation 1. So how does it look like? Therefore, what does it look like? It looks like d v of t by dt is equal to 1 by c times I of t would become. Okay, this further implies that I of t would be what? C times dv of t by dt. Okay, that means at t equal to infinity, what happens? At t equal to infinity, because we are looking at final conditions, I of infinity would be 0. Since dv of t by dt is 0. That means after a long duration, after the switch closure, if after the switch is closed for a long duration, this v of t would be a constant, v of infinity would be a constant. Understand that? So what happens? This v of infinity, you can write this as the infinity. Okay, so this is what you have to understand. So we have to summarize this again. So how to summarize? Okay, let's see summary. So what is that we are looking at? At t equal to 0 minus, at t equal to 0 plus, at t equal to infinity. So this is initial condition. Okay, so this is final condition. Now let's say there is a capacitor initially, when at t equal to 0 minus, let's say there is a capacitor. Capacitor with no current, no voltage across that. Let's say no voltage, because we are doing voltage analysis, right? So let's say there is no voltage, suppose. No voltage. So across the capacitor, no voltage means, that means what is that is happening here? V of 0 minus is what? 0. If V of 0 minus is 0, okay, V of 0 plus is also 0. So that means if voltage is 0, means capacitor is what? Short circuit. So capacitor can be replaced by a short circuit if there is no voltage source. Okay. In final conditions, what happening at I equal to infinity? I equal to infinity is 0. I at t equal to infinity is 0, we should say. That means I of infinity is 0 here. That's why we write open circuit. That means at t equal to infinity, if there is no voltage, capacitor can be replaced by a open circuit. If there is no voltage in initially at t equal to 0 plus, the capacitor can be replaced by a short circuit. Understand that? Now suppose there is a voltage across the capacitor. Okay, say V0 is dropping across this. Then what we can do? We can replace the same bar like this. Understand that? So that means if V of 0 minus is V0, then V of 0 plus would also be V0. So that means the capacitor can be replaced by a voltage source V0. Understand that? And in final condition it is shown like this. Okay, so this is how we are going to summarize. Fine, so you can just go through this once again. Okay, in all the details I have done this. Go through this. Fine, this will be something that would be considered for examination also. This is very popular question in exam. Write the initial and final conditions. Obtain the initial and final conditions for L, C and R. So we have done it for L and C. Okay, so we have to do it for R. Understand that? So initial and final conditions for R now. Okay, this is simple because I'll tell you why. Because R is not a storage element. I'll be talking about that now. Initial and final conditions for R. Fine. So what you should say is R is not a storage element. R is not a storage element. Since R is not a storage element, what we can say is current through R at 0 minus would not be equal to current through R at 0 plus. Similarly, voltage across R at 0 minus, okay, would not be equal at 0 plus. This is what is initial and final current. That means current and voltage through the resistor would change instantaneously. That means if there is a current flowing through R, that is I of 0 minus, then I of 0 minus would not be equal to I of 0 plus after the switch is just closed. That means the current and voltage would change instantaneously. Current through the resistor or voltage across the resistor would change instantaneously. Okay, because this is not a storage element. Why do we say that? How do we consider that? We say let's consider a tank here, water tank. Fine. Now, when would this water tank overflows? When would this tank overflows? When this tank is full of water, it overflows. Okay, overflows. But suppose when the tank is not full, that means this. When the tank is not full, suppose you say this, no overflow. That means there is a supply here. Okay, there is a supply here. When would this be overflowing? Overflowing is totally charged. So let's consider this tank for capacitor and inductor. Okay, if capacitor is fully charged, then only it will discharge. If the inductor is fully charged, then only it would discharge. Okay, so that's why in inductor and capacitor, okay, the charging or we should say discharge. The discharge will not happen instantaneously. The change will not happen instantaneously. Soon after the supply comes, the output will not come. Okay, whatever was the condition before there was no supply, the same condition will prevail for a while, because it takes time to fill in and then it overflows. So that's why we can these are storage elements. Okay, L and C are storage elements. We have to consider them as a water tank. Water tank only overflows when it is filled to the maximum. Otherwise, it will not. So that means it takes time to get charged and then it would discharge. So the current or voltage here will in LNC, the current in inductor and voltage in capacitor will not change instantaneously. Okay, but in resistor it would change instantaneously, because resistor is not a storage element. That's why we write this. Is that okay with you, everybody?